When most practitioners of calculus use it, they rely on rules that they have learned and remembered to calculate the derivatives. Now we've seen how to find the slope of a tangent line, and now we'll see the connection between that and what a derivative is and the limit definition of a derivative, and then we'll start to learn some rules that we can apply in practice. So our main question for this video is, what are the basic derivative rules? But before we get into some rules, let's talk about the derivative itself and how it's related to that tangent line. The derivative of a function at a point is the slope of the tangent line at that point. So what you see on the screen here for definitions are the same as the definitions that we used for finding the slope of the tangent line. So remember, there are two different formulations of that we've looked at. Either you're approaching the point x equal a, and so the denominator is x minus a, and then you have the value of the function at those two different points. And then alternatively, you can also say h going to 0, where h is the difference between the value of x and the value of a. So in other words, h is x minus a. So two different ways of saying essentially the same thing. These formula will tell you what the slope of that tangent line is. These limits give you that value. Now what I'm saying here is that the derivative of the function is the slope of the tangent line at that point. And so the notation that we've added here, f, we call this f prime, looks like f apostrophe, but f prime at a is this limit, or this limit, whichever one you prefer. And that is the derivative of the function at the point a. The derivative of a function is also a function itself, and so if you take out the a and you replace it with just an x, so instead of a particular value x equals a, you're saying what is the derivative at any value of x. You could ask what's the slope of the tangent line at any value of x. And so the derivative becomes a function, or it is a function as well. And so you could calculate it at any point within. And so when we think about the rules, what we'd like to do is have a rule for finding the derivative at any point along its domain, not just one particular value. It would be good to have a formula that works for all the particular values. If a function can be differentiated, which is the verb we use to describe taking the derivative, differentiated, we say it is differentiable, and that implies that the function is continuous as well. So if we can do this, if we can find this limit at any value of x, then the function is differentiable and continuous at every value of x. So differentiability implies continuity as well. Now, illustrating here that the derivative is itself a function, we have two functions. This is square root x, and then we have x squared minus 2x, and what the derivative would be. So derivative at any point along this curve is going to be representing the slope of the curve. So it starts out with it's going kind of straight up, so it's like really big slope. And then as x moves forward, the slope is getting smaller and smaller and smaller. So that's what we see with the derivative function. The derivative function is starting high and getting smaller and smaller and smaller as we go. Now what about this parabola? Here it has a negative slope. It stays negative until it gets to here. And at the bottom of the parabola, it has a slope of 0. And then it increases from that point forward. So here the slope is negative, so the derivative is negative, and the derivative crosses over into the positive here at x equals 1, and then it's positive going forward. So the derivative function is this orange line, and this function right here represents the derivative of this function. So derivatives are functions, and because the function here is continuous and smooth, it's differentiable, and we have a derivative at any point along the domain. Now I've shown you the prime notation here. F prime of x is a way of indicating the derivative. There are different ways. So let's remember that a function is, or can be written as y equals f of x, right? So the y value is what you get by putting x into the function. So we write y equals f of x. And then we have these limit definitions of the derivative, and we can plug in a particular function and take the limit and find the derivative function. So one notation for that is what we've been using. F prime of x indicates the derivative of f at x. And so because you've written it here like this as a function, it does tell you or indicate to you that the derivative is a function. So that's one nice thing about this notation. There are other ways. So remember Leibniz from the first video on derivatives. Leibniz was one of the early inventors of calculus, and his notation used this d over dx to indicate a derivative operation on the function. And that's to indicate that what you're doing is taking the limit as these differences between the x values and the y values get smaller and smaller and smaller. Remember that 0 over 0 problem. So you could say the differential in f divided by the differential in x, where those differentials are becoming infinitesimally small. And so this is a suggestive notation about the type of operation that is happening. So we say d by dx, or d over dx, of f of x. So it's like an operation. Now, obviously, this is the most cumbersome way of representing derivatives because it involves the most notation, characters here, to write it. The most compact would be just to say f of x gives us y. We want the derivative of f. That's just y prime. So that's the simplest way to write it, and pretty common once you get into working with calculus, rather than carrying out this extra information. If you know it's a function and you know it's an operation, you can just say y prime. Kind of a halfway in between these is to write dy dx, which indicates the operation that's happening and also is a little more compact than writing out either of these two. So take your pick, whichever one you like. Any notation is possible. I won't put it up here, but Newton had another way of indicating derivatives using dots on the functions. The way your book tends to use is the f prime notation and the y prime notation, but you'll see all of these within, and they're all equally valid ways of representing the derivative. Now finally, we can get into the rules of derivatives. And for this first rule, I'm going to actually show you the proof of it. For the other ones, proofs are in the book, and I would encourage you to go look at them there, but I'm not going to go through them in the video. You'll see there that there's quite a bit of algebra to prove these rules to be true. But let's look at the constant rule, which isn't too much work. So we're saying a function is a constant. So f of x equals c, c is a constant, then its derivative is equal to 0. So if the function is constant, its rate of change is 0. I might not even need to go through the proof, because that should be kind of obvious given what the derivative represents. But let's see it anyway. You plug in the function at x plus h. Well, it has the same value at any value of x. So whether it's x or x plus h, the value is going to be c. So you have c minus c over h. Right? The value of the function here and the value of the function here are the same. Okay, so it's 0 in the numerator, but also 0 in the denominator. So what happens as h goes to 0? This one just works out to be 0. No matter what 2 points you pick on the function's like if you were to draw the secant line, its slope is always 0. So it's going to be 0 as you make your way back to the original point. Okay, so constants, zero derivative. What if you have a power? If you have the power of a function, like f of x equals x to the n, then what do? Well, the rule there is that you can bring the power down in front and subtract 1 from the power, and that gives you its derivative. So here it is written out, f prime is n times x to the n minus 1. So if the function is x to the n, bring down the n, multiply it out front, subtract 1 from the power. So every time you take the derivative of a power, you reduce the power by 1. You can also express this in this notation where you're like doing the derivative operation on this function, same result. We'll go through an example at the end that pulls these rules together. All right. Many of the functions that we look at are combinations of things. Combinations meaning sums or differences or multiplications. Now, if you multiply two functions together, you have the product of two functions. We'll talk about that next time. But if you have a constant multiple, we'll talk about that here. So for these definitions, we're assuming we have at least two functions, and we're going to call the two f and g. We're going to say you can take the derivative of them, and then let k be some constant. It could be any constant. And then we'll go through. This slide has the sum rule. The next slide has the difference rule and the constant multiple rule. So if we're taking the derivative of the sum of two functions, which is what's written here on the left, we're doing the derivative operation on f plus g. The rule is you can just distribute this through. So the derivative operation is distributive. You can just distribute it through, so then it becomes the sum of the derivatives. So the derivative of the sums is the sum of the derivatives. Okay, so pretty simple. The difference rule is essentially the same. You can distribute the derivative through, and so the derivative of the difference is the difference in the derivatives. So you can just put it through. Now, lastly, constant multiple rule. What happens if there's a function and then you're multiplying it by some number, like 3x squared instead of just x squared? Well, if you take the derivative of a constant times a function, you can just take the constant out. Remember, the derivative of a constant is 0. So the constant just multiplies the derivative just like it multiplies the function. Okay, so sum and difference rule and constant multiple rule, we can put those together with what we now know about the power functions and constants, and take the derivative of something that puts all of these ideas together. Okay, so last slide here is this example. We have an arbitrary polynomial, 2x cubed minus 6x squared plus 3. What is the derivative of this function? Now, as you're learning this, you might have to think about this step by step. If you've been doing this for a while, say in like the next couple of weeks, after you've done a few examples, you will look at this function and you will immediately be able to write down the answer. But let's take our time. So this function is built from this minus this plus this. And what we've learned from the sum and difference rule is the derivative operation. So if I want to take the derivative of this, it's really just the sum or difference of the different derivatives. So I take the derivative of this, I need the derivative of this, and I need the derivative of this. And I can do this minus this plus this. So that's how we can use the sum and difference rule. I've got powers in here, so I need to use the power rules. I've got a constant, so I need to use the constant rule. And I've got constant multiples. So this one example includes all of the rules that we've looked at so far. All right, so let's take the constant. The derivative of that is 0. And now let's look at the powers, x cubed and x squared. X squared will give me 2x. Take the power, put it in front, becomes 2x. x cubed becomes 3x squared. Take the power, put it in front, and then subtract 1 from the power. 3 minus 1 is 2. Now we also did that over here. I glossed over it, but 2 minus 1 is 1, and you don't need to write the 1. So derivative of x squared is 2x. Derivative of x cubed is 3x squared. Now what happens because of the constant multiples? This is 6x squared and 2x cubed. 6x squared, remember the constants out front just go along for the ride. So if the derivative of x squared is 2x, the derivative of 6x squared is going to be 2x times 6, so 12x. And then here, instead of just x cubed, we have 2x cubed, so I need 2 times 3x squared, which is 6x squared. So now I have the derivatives of all the different pieces in here. 2x cubed, 6x squared. 6x squared, 12x. 3, 0. I have the derivative of all these pieces. I just need to put them together using the sum and difference rules. So 2x cubed becomes 6x squared minus 6x squared becomes 12x, and then plus 3 becomes 0 when you do the derivative operation through. So 2x squared minus 6x squared plus 3 has the derivative 6x squared minus 12x plus 0, which you don't really need to write, but put it there just to illustrate completely what we did. All right, so that is applying these rules. Take some time to practice doing examples like this, and you will pick up the rules very, very quickly.